Now, the next speaker is Katarzyna Krzyzanowska. So, Kasia is a senior researcher at Los Alamos National Lab in the quantum technologies team. So her research is focused on ultra-cold atom systems, in particular BEC guided in optical potential for quantum sensing and quantum computing. So please, Kasia, you can start.
Thank you very much. Good morning, good afternoon, and good evening to everyone. I would like to first thank organizers for this for the effort preparing this wonderful workshop. Also for an opportunity for me to talk today on behalf of the team that I am part of. And so I'm a part of quantum technologies team at the Los Alamos National Laboratory, based in New Mexico. Our team currently consists of 2 staff members, Malcolm Bosher and Mike Martin, 8 postdocs, and 2 students that stay with us for the summer. We have many various projects and never enough people to work on them. So I just would like to make a remark that we are always looking for new faces to join us. And just to encourage, I can say that Los Alamos is placed in a really beautiful place in New Mexico, just next to the mountain range surrounding, fortunately nowadays, inactive volcano. The work I'm going to talk about today is just one of our projects that belongs to Malcolm, and a project that a few of us work on. And the structure of the talk is going to be rather standard. So I will first outline what was the motivation, the background for what we are doing and why we are doing. Then I will discuss the experiments and the results for 2 implementations, two different configurations, which is Atomtronic rotation sensor using the rubidium atoms, and the Atomtronic accelerometer using the potassium. Then I move to summary and the outlook, so what we are planning in the foreseeable future. So I will open the talk with quite a bold statement that everything started when people realized that we need an improvement of inertial sensing, especially in particular rotation sensors. And why is so? Well, it's because there is an idea that in an absence of the GPS signal, one could potentially use the inertial sensing consisting of 3 accelerometers and 3 gyroscopes to integrate the output of those devices twice and calculate what's the final position, knowing the initial coordinates at the beginning of the travel. However, it's not actually that easy. And here, just to show why, I have a plot where I show what is the estimated position error for devices, current technologies devices, over the time that we are being offline and we are using this kind of system. So as you can see, the position error grows to an order of hundreds of kilometers over a scope of just a few hours. So if one would try to use it as a navigation system on a submarine or on an airplane, one would surely eventually get lost. And it turns out that the main contributor to this noise is our gyroscopes and imperfections of the gyroscopes. And so the standard approach to modern gyroscopes is to have a light source, laser light that emits a beam, which is then subsequently split on a beam splitter into 2 interferometric arms, which enclose the area in between those arms, and then recombined on the detector where we can see the interference pattern. And if the device is rotating, the phase of the final interference pattern here, known as the Sagnac phase, because it's a Sagnac effect, is proportional to the rotation of the rate of the device. The area enclosed by the arms, interferometric arms, as well as the energy carried by the particles used in this kind of experiment. So one could think that actually if we use particles that carry more energy, for instance, atoms, since they're very heavy, atom sonic interferometer could promise, give us a significant sensitivity improvement. In principle of the order of 10 to 10, but it's obviously ignoring some technological challenges of different platforms such as light and atoms. We have heard so far during this workshop, especially during last talk of Philip Boyer during last Friday, that there has already been a spectacular achievement showing that Freespace devices, Freespace atom interferometer can show to be useful in many cases. So what I mean by free space in this case is a situation where we can trap atoms, then release them into a free falls, then expose them to a series of light pulses that serve as a splitter, mirror, and splitter, which manipulates the momentum state of the atoms, creating something like Mach-Zehnder interferometer, and then measure the different spaces in the two ports, interferometric ports at the end. So this kind of technology is really already impressive. It is mature, it has been taken to the field. It has been even tested in extreme conditions like on the airplanes here in 2011 by Philip Boyer's group. However, there are certain limitations and challenges for this kind of platforms. And the first one is what happens if the platform that the device is installed on moves too rapidly. Well, since the atoms are in a free fall or free space, if the device, let's say, rotates too quickly or accelerates too quickly, the atoms will simply smash against the wall of the vacuum chamber, and there is no signal to read out at the end. So there is one of the fundamental limits. And also those devices, it's difficult to reduce their size, weight, and power. They tend to be rather big, and especially for the rotation sensor, if we want to get the biggest and close area, we actually need to increase the interrogation time of the free fall. And that just means that the devices are getting pretty big. So what's the possible solution? Perhaps Atomtronics that would allow us to confine atoms to a certain space and then manipulate their properties for our advantages. There are a couple of optical technologies for Atomtronics. So the one that we have capabilities of in Los Alamos National Laboratory is the painted potential. We also heard of the other ones, such as spatial light modulator or digital micro mirror device. Also, we've heard many wonderful talks about techniques that use those particular devices during the past week. We might consider them, but what we can use right now is the painted potential, which is simply a time average dipole trap potential, which is crossed with the light sheet. So we have a beam, red detuned beam, which is being scanned very quickly to create arbitrary shape potentials. And we in our group have used this technology to show certain approaches towards Atomtronics with painted potentials. So we were able to show that if we paint a junction, so like Y-split junction, we are actually able to demonstrate coherent waveguide beam splitter when the BEC initially launched with some velocity can act on this junction and then be split into two coherent clouds. We also were able to demonstrate the Atomtronic squid, where we painted the potential in the shape of ring with two Josephson junctions, and we were able to show that in this configuration we have a clear Josephson effect with ideal junction, as well as we have quantum interference of currents that were induced in this system here on this graph, this oscillation. I don't have really time to talk about it. I just wanted to mention that this is one of our capabilities. So you are more than welcome to ask about it or follow the papers I have listed it here. What I am going to talk about though is a little bit more practical approach to rotation sensors. So the approach I just shown on the previous slide there are a few main challenges that arises. So first of all, we would like to have a single mode propagation of the atoms in this kind of systems. We are aiming to get long interrogation times to get the higher sensitivity. And also a smoothness and the stability of the potential typically is an issue. I mean, one needs to work very hard in order to provide very smooth and stable potentials, which is possible. But our solution, there is a possibility to use a different scheme to tackle those problems. For instance, schemes that are based either on different geometry or they are quantum enhanced. For instance, quantum solitons in lattice rings, which are proposed by Anna Minguzzi and Luigi Amico. This is something we are considering. However, for now, and the work that we've been focusing for the past 2 years is a technique known as a waveguide interferometer, where we prepare a BC and we propagate BC in a waveguide formed by a single collimated laser beam, which then we get to translate in space. And this is how we are going to realize our interferometer. So the experimental setup. Here to the left at picture A, you can see a scheme of what's going on in the experiment. So we prepare the rubidium BC in cross dipole traps of the waveguide beam. This is the long one, and the vertical beam. Both are 1064 nanometers and about 60 micrometers in waist. So we prepare the BC in magnetic insensitive state. You can see that the waveguide beam goes through an AOM and a lens, and that allows us to ensure that as we scan the deflection frequency at the AOM, we can ensure a parallel translation of the waveguide during our interferometer cycle. This waveguide is overlapped with a standing wave beam, 780 nanometers, which is formed by a beam that comes here and it's reflected by a dichroic mirror. And this beam is used to achieve Bragg pulses, during the interferometer. So here on picture B, we can see what's actual sequence that we use. So we prepare, after preparing atoms in the waveguide, we use a double square pulse to split the atoms into 2 wave packets. So it's a superposition of 2 wave packets propagating in opposite directions. And as they propagate in the opposite direction, we start moving, translating the waveguide in space outwards. As we do it, we use the reflection pulse to change the direction of the wave packets. Then when they go through each other, we change the direction of the waveguide, start moving it back towards its initial position. We can reflect it once more, and when the atoms are overlapping in this initial position, we can apply, the recombination pulse, the same as the splitting. We allow the cloud to evolve with time, and what we get is this kind of pictures over here, where we have atoms and 2 output ports. The one output port is everything is in the middle with atoms with momentum equal P0, and the second port where atoms have a momentum ±2 h bar k. So this way, by splitting and moving the waveguide at the same time, we enclosed area. What we can do, we can scan a frequency, we can scan a relative phase of the final and the initial pulse of the splitting and recombination, and by this way we can recover the we can scan the interferometer phase and recover the interferometric fringe. Another important technique, just wanted to point out, maybe these are actually our experimental data taken for this very purpose. Another technique that we use as very important for us is delta K cooling, as because this technique allows us to minimize the expansion of the cloud of the condensate during the interferometer cycle and the final measurement. And I just have here to the top right to again remind what our setup looks like. just to point out that the BEC is initially prepared in a cross dipole truss by waveguide and so-called vertical beam. So here I can see the initial size of the cloud when it's prepared and released from the BEC. We can switch off the vertical beam while still keeping the atoms in the waveguide, and by allowing it to expand by for tens of milliseconds, we can create a diluted cloud. Then subsequently, we can apply a short pulse of the vertical beam once again to give it to apply the delta cooling technique. And as you can see, at time just after delta cooling, this is the size and the shape of the cloud, and up to 100 milliseconds after that, we still have pretty well collimated condensate. And here to the left, we actually have a comparison of the cloud expansions with and without the delta cooling, and we can achieve temperatures as low as 300 picokelvins. That is pretty much essential in our experiment to get a very long coherence times, as I will explain later. Well, okay, now it's exciting part, which is our results. I'm going to start with the one of the most significant, I would say, achievements, which is a measurement of the Allen deviation. So for those of you who are not familiar with Allen deviation is a measure of stability of the device. In other words, for how long one can keep accumulating measurements of single value and keep averaging it down before and still recover the true value of the measured parameter before any kind of drifts and instabilities take it over and introduce systematic error. So we have measured the Allen deviation for 3 configurations. I mean, I have 4 curves, but I explain in a second why. So those 3 configurations is 20 milliseconds static waveguide. By static, I just mean it's not moving, it's fixed in place. 80 milliseconds moving and static. So first, let me explain why do we even bother to take 20 milliseconds static waveguide. This is kind of our benchmark that allows us to measure the experiment once in a while after various kind of improvements and so on in the experiment, and make and check the performance of the experiment compared to the previous time. So as you can see, we had a certain curve here for Allen deviation in 2019, which was kind of taking off at some point. And in 2020, we managed to increase the interferometer cycle, reduce a little bit the Allen deviation, and also this feature at the end seems to be gone. And now we also measure the Allen deviation for 80 milliseconds static and moving waveguide. This is the green and blue curve, and they correspond to those fringes that I can show here at the top. And what is important is that those 2 curves are very similar. That means that moving the guide does not introduce any effects into our system, which is great because that means that we can trust our stability of our system. Also, the Allen deviation scales as 1/√of tau, which indicates white noise in the system, at least up to 4,000 seconds, which is a couple of hours. It's pretty long time. Those measurements were taken over a day or 2 per each curve. And also, looking at those curves, we think that we know that the sensitivity at 100 seconds is below the earth rate. So we think we should be able to measure the earth rate here at New Mexico using this device. So we have tested different coherent times. And here I show 3 cases, 3 fringes for 20 milliseconds interrogation time, 40 milliseconds, and 80 milliseconds. I would like to point out that those numbers is the total interrogation time as we are moving back and forth the interferometer from the splitting to the recombination pulse. So you can see that the interferometer fringes, the contrast decreases with time. But if we look at the raw data here below for each of the fringe, it is clear that the decrease of the contrast mostly comes from the phase fluctuations that increase with time. And so the question is, well, where does this phase fluctuation come from? Because, well, yes, sure, we are able to recover pretty nice fringes, but at the cost of measuring and averaging them for a very, very long time, which obviously in practical interferometer is not possible. So we actually know where does the phase noise come from. And it comes from the position, or actually the fluctuations of the position of the retromirror, which is forming standing waves. So here to the right on the top, again, I recall the experiment. And you can see that we have standing wave, which is formed by this retromirror. And the position of this retromirror tells us or designates what's the phase here at the position of the atoms. And so if the mirror moves or jitters during the interferometer cycle, we are going to introduce the noise. And in fact, for long interrogation time, the phase noise is so big that it reduces significantly the fringe quality. So here to the left, I can show 120 milliseconds fringe quality, where we have about 10 measurements per 1 point, and we can't really recover the fringe, even though we know what are actually the parameters, such as frequency of the fringe. So we use
10 minutes.
Thank you. Okay. So we used a technique. We used the accelerometer to estimate the phase noise following work of Philip's Boyer's group. I can show it here. It's a very first attempt. It's very crude, where you can see this is the retromirror, and we mounted the accelerometer not even on the retromirror. We just mounted it on the same substrate. The reason why we did it is because we didn't really want to disturb the experiment by taking apart some parts of the optics. It's not going to be that easy to fit it there. The experiment is a bit busy. So using this technique, we are able to estimate phase corrections for each of the measurements on the plot to the left. And using that, we are remarkably able to recover actually fringe 120 milliseconds interrogation time. That corresponds to 2 squared millimeters. And that's pretty fresh result. We are very happy about it. It's about a factor of 4 more than the most reported area so far. Yeah, so we are happy about this particular result. Well, we have done a couple of other things too to investigate the performance of the experiment. And so we tried to see what happens if we have multiple round trips in this kind of system. So by one round trip, just to recall, what I would like to say is by one round trip, what I understand is the cycle during which we have 2 reflection pulses and the waveguide move outwards and back to initial position. And so I would like to point out that here, during one round trip, the wave packets, they have a chance to go through each other once. And since we are using rubidium atoms and we have interactions, pretty strong interactions, the question for us was how many times can we make the clouds go through each other and still see a coherence in our system. So this is essentially what the slide is about. We tried from 1 round trip to 5 round trips, where 1 round trip is 20 milliseconds. So the first row here corresponds to 20 milliseconds of the interrogation time. And the 5 round trips here corresponds to 100 milliseconds interrogation time. And as you can see, we still have coherence after 5 round trips with a big with quite a significant interactions. What happens is that the contrast of the fringes reduces as we do it multiple times, more than just because of the interrogation time total. So there is an effect of the scattering. Well, we can't do much about it using rubidium atoms, but what we could do, and we did, and actually I would like to credit my coworker here for this work, Joshua. We could use the non-interacting gas, in this case it's rubidium-39, to show that we can actually achieve long coherence time. So potassium-39 BC has a very convenient flashback resonance that allows us to tune interactions through zero with a magnetic field. So here, this picture to the bottom left shows the number of atoms that remain in the BEC after certain after n reflections for different scattering lengths. Here, the purple line, which corresponds to 150 Bohr, is comparable to what we have with rubidium. It's about 100. And as you can see, very quickly, within a couple of round trips and reflections, so as the atoms go through each other, we lose many, many of the atoms. However, if we tune the interactions close to zero, then the only residual loss rate is entirely due to imperfections of the mirror reflectivity, which is still about 99.9% in this case. And so using this technique, we're able to observe over 200 round trips and a second coherence time in a linear interferometer in this system. So it's shown here to the right, where we have two interferometric fringes, one for the 1 round trip and the second one for 200 round trips. And the contrast that we can recover from that is simply remarkable. We are very, very happy about those results. It's all in preparation to be published. And so it's probably, we have more, probably we could talk for longer about what we've done. But I think it's time to actually summarize the most important parts of our achievements. So we have demonstrated an Atomtronic rotation sensor using BEC propagation in optical potential. And we did it showing up a coherence of time up to 160 milliseconds and enclosed area of 2 squared millimeters. We showed also we have Alad deviation that scales like 1 over square root of tau, indicating white noise up to 4,000 seconds, and that we should reach Earth rates. It reaches Earth rate sensitivity in a few seconds. We also showed multiple round trips and investigated this, the effect of multiple round trips and interactions in this kind of systems using the rubidium atoms with 5 round trips and 200 round trips using non-interacting potassium machine. And using the non-interacting potassium machine, we show that the coherence time can be over 1 second. So what we are planning to do in the future, we would like to increase the interferometer area. And what we could do in our current existing experiment, we could increase the interrogation time by improving our current methods. So the accelerometer and delta key coding, there is still room for improvement. Also, we are planning to use strontium in order to get a system that is very weakly interacting, I mean, close to actually non-interacting potassium, in order to get multiple round trips and this way increase the area. We are also planning to measure a rotation sensor about multiple axes because right now we just move it horizontally. We would like to study and compensate for effects of tilt. So far, we make sure in the laboratory conditions that the waveguide is pretty well leveled. And we would like to also characterize all the systematic effects. We are aware of many of them, but we are not at the stage that we could, let's say, characterize them and just take out from the fringe whenever we have some systematic phase shifts. At this point, I would like to thank ALDRD and DARPA who found our work for the past 2 years and say thank you very much for listening.
Very good, Kasia. Thank you very much.
Thank you very much.
There are questions from the panelists. So the first question comes from Maxime Orshani. Please.
Right. Hi. Thanks for the great talk. So I have a quick question to the very beginning of your talk, to the painted Y junction. So yes. My eye is looking for a second input channel because I mean there are hundreds of theorems like conservation of a trace of a S matrix and so on and so forth. So what will happen if I beam split, reverse time, and change the phase by pi in one of the output channels? I mean, where would the atoms go to the first excited transfer state of the input waveguide? I mean, I want there are theorems that tell that the number of outputs must be equal to the number of inputs. And so I'm looking for the second input.
Oh wow, that's actually a good question.
I have a guess that this is the first excited transfer state of the input waveguide.
Yeah, so I discussed it once with Malcolm a long time ago. I must admit that here I mentioned this work, but it's not something I worked myself and particularly on.
Okay.
I'm going to use those techniques. Is Malcolm here perhaps? If he's here,
yeah, I can answer that. So Maxime, yes, you are right. You know, if you imagine recombining those two BECs after you put a pi phase shift into one of them and then bring them back together, it's going to form the lowest energy anti-symmetric state, which is it's the transversely first excited state of the guide. So ground state and first transverse excitation are the two ports of the interferometer.
Yeah, no, great, thanks. And I just wanted to mention that Rick Heller at Harvard, so he has a series of rigorous theorems about related to all that. So it's I mean, this is where I developed my intuition from. Thank you.
Okay, so my question is mainly about the Bragg beam splitting process that you suggested. So you mentioned that you diffract to the left and right. So maybe could you elaborate on this process? You also drew like two box pulses in there. So is it like a composite pulse, or how do you realize the process?
What we have is 708. I'm sorry, I'm going to say response in a comprehensive way because I'm not sure precisely which part I should elaborate more. So what we have is a wave 780 nanometers, which then is overlapped with the atoms and reflected by the dichroic mirror. So what we have here is a standing wave that just propagates, right? A standing wave that the BC is exposed to. And so if you create a certain kind of pulse shapes and with a certain area, what you can do, you can ensure that the beam splitting you create, it's a superposition of the atoms going into one direction and the other direction. Well, it's, I mean, from a physics point of view, the understanding is that it's because let's say the atoms have more probability to be scattered into one direction or the other. It's basically just a beam splitter in this case. So this is not the only way to create beam splitters. We could also create different shapes and pulses, but that's following a paper. I don't have a reference here. I could show you, I could send you the references if you're interested.
Okay.
Yes?
Yes, thank you. Yeah. So if I understand correctly, it's do you have any population left in the p=0 momentum state?
Well, so yeah, that's the point. We have very good splitting ratio. I mean, we can't see any atoms left behind in the population p=0. We can tune the efficiency of the process by well, checking for the area of the pulse that we are sending. So essentially, we just tune the power of the pulse that is applied to those atoms. And this way we can observe the Rabi oscillations. So we can select the first Rabi oscillation and just make sure that all the atoms are gone into ±2 h bar k. And yes, we don't see any atoms left in the p=0 population.
Okay, thank you.
Thank you for the nice talk. I have a question related to the previous one. What would there be any benefit in giving it a bigger kick, maybe ±4 h bar k, to increase the area of the interferometer?
Well, yes, that's one of the ways we could go for. And we actually have studied a little bit higher momentum kicks. The problem, though, was that the efficiency was not as good as using just 2h/k, because as I said, for 2h/k, we have no atoms left in P and momentum equals 0. Whereas for higher splitting, we had some population left, and also the mirrors were not perfect. And we had basically many wave packets just traveling everywhere in the waveguide. So we started preparing for that, and we have an idea what's going to happen. But I think that would require more work in order to recover as good contrast as we can recover for 2h/k.
Right. I think that I think you can have tailored pulses that will give you, or maybe sequences of pulses that would improve that. But it's not really my area. But I was just curious. Thank you.
Yeah, I think it's possible. We haven't investigated it thoroughly enough to know what sort of approach should be taken.
Thank you.
Okay, good. So I would read the question from the Q&A. So it's by Albert Galemi. Hi, Katarzyna, could the loss of contrast in the oscillations due to interaction be used in order to get an estimation of the compressibility of the system? And second question, is your setup suitable for spinor or two-component systems?
Okay, well, maybe I will start with the second question. Okay, let me read the Q&A.
Yeah, Q&A. Q&A?
Yes, I'm in Q&A.
Yeah.
And second question is, your setup suitable for spinor or
two-component systems?
Well, we prepare in this experiment atoms in magnetically insensitive state. And the reason for that is obviously because any kind of exposure to external fields could impact our interferometer. However, during the preparation of the BC, we could actually prepare BC that consists of MF equal -1, 0, and 1. It's just that during the preparation, we get rid of those of -1 and 1 components in order to have purely in magnetically insensitive state. So yeah, I think we could have different components for MF. In this case, I think would also pump to different hyperfine structure, hyperfine levels, but it's not something that we really considering doing recently. And the loss of contrast, could the loss of contrast in the oscillator be used in order to get an estimation of the compressibility of the system? I'm actually not sure. I mean, what do you actually mean by the compressibility of the system in this case?
I was well. I mean, when you have a system that has interactions, in principle, it has a compressibility. I mean, my question is, since you have this effect that is due to interactions, my question is if you can use it in order to measure the compressibility.
Well, we haven't tried. I'm actually not sure. I could give it a thought. I'm really sorry. I could give you more specific answer on that.
Okay, no problem. Thanks.
Okay, so I would thanks Kasia again, and move to the next speaker.